Okay, thank you, Will. Let's get started. And so, for this is like a fairly large effort in a sense, in that many people are involved, and we're now finally getting to some decent result or interesting thing that can be shared, I would say. And as Will said, like the idea is to try to first somewhat evaluate the whether like DAS in this way or distributed acoustic sensing instrumentations are viable and useful for earthquake monitoring. And the second is to see how we can make it operational for existing seismic networks, such as the Southern California Seismic Network. So let me give you a little bit of an overview of the things that, everybody is familiar with this more than myself probably. But as we know, for a modern earthquake monitoring workflow, what we have continuous seismic data, and I will go actually a little bit more into the details of this. And what we do is that we have a constant flow of data into like some processing machine. And what we have to do is to detect whether there is an earthquake or not at the current time that has been streaming data, find P and S phases, polarity, and other thing, and try to associate all these peaks and information, locate an earthquake, estimate the magnitude, potentially like go even further for good quality events, go to focal mechanism and moment tensor. So, and eventually, I guess like the output of any earthquake monitoring workflow is a catalog that is used for evaluating risk and for scientists to try and understand what's going on underneath the surface. So, and in this talk, I would like to, give a little bit of a sense of what we're going to discuss besides earthquake monitoring. Of course, it's how we can use distributed acoustic sensing instruments, basically like instruments that are connected to fibers, and they measure the deformation of the fiber at a fairly good resolution scale, like we're talking about meter scale level. And we basically send a laser pulse into this fiber. And with interferometry, some laser power is scattered back at every section of the cable. And we can perform basically like the measurement of how much the cable in a given section is deformed. And if there are questions at the end of the talk, I can answer more questions about the specific details of the instrumentation. But the basic idea is that you connect this instrument to an existing fiber, and it can transform this fiber into a dense stream meter instrument at very, very long range, actually. Like modern instrument, we have one instrument here that can go as far as 160 kilometers, so almost 100 miles. And the beauty of it, and I will go more a little into the details related to California, is the fact that you can connect this to any fiber, really any fiber that can transmit the light, and particularly like single mode fibers. And as I said, like basically, like from this, what you have from one single instrument that takes very little time to deploy, you can get thousands of channels covering tens of kilometers. And you can actually also see from a research perspective how much impact DAS is having in geophysics in general. And this is just a nice review paper by Feng Cheng published last year, where they review with how much citations and publication have been going on over the years. And really, like before 2010, like DAS was not like super popular, and then like after the oil industry started using DAS for real, and after some time also like the scientists started to realize the power of DAS for other purposes. And to give you a sense how much of or how many fields and topics are covered by DAS, this is like a nice image again from that review paper, where you can see how many topics are touched by DAS. And you have a variety of topics and science point that could be touched. In particular, in this talk, we're going to talk about particularly, of course, seismic networks, earthquake monitoring, and towards the end, we're going to touch a little bit on ground motion, especially like it will be relevant for potentially like magnitude estimation with a conventional system, as well as earthquake early warning. And to give you a sense of how pervasive is this fiber network, how much fiber there is in California, this is like a map showing like some are planned, some are actually already there, and you will see some are actually being used right now. But this is the middle mile fiber route that is part of a big effort for California to have fiber telecommunication all over the state, and as well as some of the submarine cable that are departing from California coast, and especially like here, actually there are like many different cables present in Los Angeles, and it will come to an important point at the very end of the presentation. So DAS research at Caltech, thanks to Professor Dongwen Zhang, has been actually like I think one of the leading figures in this topic for seismology. And in particular, like a lot of research has been done on trying to estimate magnitude from DAS recording. Also, we also worked together with Wei-Chan Zhu, another postdoc that was here and now professor at Berkeley, where we developed PhaseNet-DAS, which is a machine learning tool to pick earthquake travel times from DAS system. And will be like a crucial point in the presentation. And a previous postdoc working also with the network, Jushun Ying, they started looking into how early warning could be effective for some submarine cable in Chile in this case, and they show how it could play out for an early warning system. But one thing that I would like to point out is that at Caltech, I've been part of Caltech for the last 4 years. This is actually, I'm starting very soon my 5th year at Caltech. And we've worked with a lot of DAS systems, actually. These are like some of the systems that some are still running. For instance, like the Mammoth Lakes here are still running, up and running. Ridgecrest South, which will play a role in this presentation, is also running and is being incorporated into the network partially, if you may. And so we have quite a bit of experience on dealing with this kind of data, as you can see from this map. And as I said, like particularly like today, we're going to focus a little bit on the Ridgecrest array, which maybe some of you have seen our previous presentation on the topic. Why Ridgecrest? Actually, it's first, full disclosure, it was already there and it was up and running very nicely. Like I actually helped set it up. And but it happened that it's covering like a nice little gap in our seismic network here. Not a huge gap, to be honest, but as some of you have seen, Igor here has done some interesting work on how latency is actually affecting some of the station in this area, especially this is during the 2019 Ridgecrest earthquake, and where you can see that once the strong ground motion started for the earthquake, like some of the station, not all of the station, some of the station started to basically getting like a big latency gap, or basically like the data were coming to Caltech at a very delayed time, and you can see like sometimes even like up to 30 seconds. So that's the reason why we thought, okay, like actually this array could be a good place to see and evaluate also like the reliability of the telemetry. One thing that I didn't say, actually, these are all telecommunication fibers. Most of them are underground, so they can record earthquakes. And the beauty of it is the fact that we can rely on high-speed internet. So, and that will actually come later in the presentation. And just to give you a sense, like again, you all are probably more expert than myself, but just to give a frame of how we insert one channel actually into the system to test, I want to give an overview of the AQMS workflow. We have, as I said, we have seismic data streams coming to Caltech. They come to 1 second buffer of about 100 hertz, most of them, and they place into earthworm wave rings. These are then streamed and multicast into the AQMS picking system. There is an AQMS associator. We can get whether there is an earthquake or not. And after that, we have some additional workflow to potentially refine actually locations. And this is actually something that Gabriel Tapp pushed quite a bit using PhaseNet, a machine learning tool to pick on seismic station. And she's done a really great job on put it into, real life. And of course, like then we can further obtain more information from the catalog, such as focal mechanism and moment tensor. But this is kind of like, again, just a brief overview of what earthquake monitoring looks like. And now, as I said, like the focus of this presentation is what is the role of DAS into this existing ecosystem, if you may, and what kind of impact it could have for earthquake monitoring operation. And again, like in this presentation, I want to focus the fact that we want to show that DAS could be placed into the existing workflow and run in real time. In particular, actually, as I said, like we rely on high-speed internet, and the more you pay, the higher the bandwidth, so we can push more actually. But the idea here is what we started to do, like when I started the seismic network, was to try to stream data in real time back to Caltech. And right now, actually, like we've been streaming very reliably, actually quite reliably, real-time data, 5,000 channels. This system is covering 80-kilometer distance. It's composed of about 10,000 channels. The data are being recorded at 100 hertz. And what's happening here, we actually saw that the best for us is to stream 5,000 channels at 100 hertz. And we stream one time sample for all the channels every basically hundredth of a second. So every hundredth of a second, our machine here back at Caltech, it receives a time sample from all the channels, okay? And then I will show we pack them in a given way to be able to incorporate. One thing that I want to mention is the fact that while we stream all the 5,000 channels, we thought, of course, we don't want to overwhelm the existing system. And we decided to just say, possibly like we can just test to incorporate some of the channels. And specifically, like we went very naively, we selected 18 channels spaced about 5 kilometers each. And these are actually like then tested for some streaming. And particularly, like I will show, like there is one channel that is being tested, which is kind of the best channel, if you may, which is the channel number 2 here, and it will come later in a second. And the fact that actually, like we, as I will mention later in the presentation, these waveforms are actually like being archived, and they can be used by our analysts to evaluate whether DAS records very well P wave and S wave. This is an example of an earthquake on the Jiggle window, where you can see this is the P wave and this is the S wave coming. So it's we got some positive feedback from our analysts. Now, in a practical manner, like what we are doing is, and I didn't mention here, but we're using like an interface with Python to interface with Earthworm. But basically, like the data, the raw DAS data stream are collected at Caltech and slightly processed into 1 second buffer, 100 hertz, and then they're placed into Earthworm rings. It's effectively like we have one channel to test whether this thing is working, and it seems to be working fine. And we basically have this channel being tested to see whether it's working properly and it's not affecting the system at all. And it's not affecting the system, of course. Now, on the metadata side, that it's very important, especially like when we look at seismic networks, we decided to follow, because we are streaming just few channels into our system, if you may. We thought, okay, we need to come up with a way to decide how to name the channels. And we just went with a SCSN metadata naming system, where we basically have the usual MSID code, where we have a network, CI, it's for seismic, our seismic network. And then we have the station code. In this case, we went very naively, like D stands for DAS, R is for Ridgecrest, S for south, because actually there is another fiber that we're thinking to use that could go north. And 01 is just one of the many channels that we're using. So 00 is the closest to the instrument, and up to 07 or 17, which is the furthest. And then the location code, we didn't use it. It could be helpful to use it in the future. And we went to the channel part, where basically we just use this usual naming, which is H stands for 100 hertz per decamant, high rate, S strain. And then we decided, let's assume like an arbitrary component 1. And as you can imagine, the strain is actually along the fiber, so it's changing as function of the position of the cable. And again, it's a very simple way, but it's at least it helps us to put this system into the ANSS Station Information System, or SIS. And so actually, like it's there, and it's within this database, which is very good. The other thing that we kind of developed early on. I developed when I was when I started at Caltech. It was how to locate this channel accurately and in a very, very efficient way. And the idea we came up with was to just drive a GPS tracked car. And this is a big car, of course, the bigger the better in a sense. And the idea is to, from the DAS recording, you can see actually this is some recording from Mammoth Lakes, just to give you an idea. This is a highway. You can see very busy highway. This is distance, by the way, or channel. And these are basically just time. And you can see that knowing the location of the fiber, more or less, and the location of the car, we are able to basically find our car and locate each channel very accurately. And this is actually like how, after you know the location of each channel, you can track your vehicle very well, and you can see how well it's tracked. And we published actually a SRL paper about it. We're sharing the code and all the procedure that we use to do this process. And by the way, we've done this process, I think, like almost 7 times or even more, even in locations far away from it. Once in Iceland, actually. And it seemed to be, and the other, maybe the craziest location, it was South Pole by Zone 1. So we did this thing many times. What about, okay, let's look at a little bit how the performance of earthquake monitoring. And this is like not in real time. So, but we wanted to evaluate how basically like the peaking algorithm was working, and in particular, like the PhaseNet-DAS was working, and how fast it can work on for some earthquakes recorded on the Ridgecrest array. And this is again like a 3.6 earthquake that was recorded by the Ridgecrest array. And the idea here is just to have basically just on top, you have a rolling window of data. This is a 30-second rolling window. And here we are trying to evaluate. It's kind of a mixture between monitoring and early warning, but we wanted to get a sense of how it was performing. What's happening here in this simple animation, we have a 30-second rolling window that is running every 1.3 seconds. And every 1.5 seconds, I'm actually applying PhaseNet-DAS on this window as if the data are streaming and coming to Caltech. And one thing that we're using is actually like a fairly decent GPU card to do the peaking, because this is a machine learning tool, a neural network tool, and it only takes 0.8 seconds to basically process and get the travel time peaks. The peaks in red are like the travel time peaks for the P wave, and the blue one are for the S wave. So you can see how well it's tracked, the onset of the waveform. In this part, actually, like we are trying, this is the catalog location of the event. And as more data come in, you can see that how well the earthquake is located, even just by simple DAS. And this, another thing that we're doing here is to estimate the magnitude with a particular magnitude estimation scaling relationship that we develop for DAS. This is just DAS. No station are included in this simple demonstration. But we wanted to get a sense of computational cost in case we wanted to start doing real-time processing. And in this case, we have this code that will also do location, does location and magnitude, and it only takes 0.4 seconds. So it seems that it's viable for real time. And one thing specifically for this circuit that worked very nicely, from the initial detection to the reliable magnitude estimation, it only takes 2.5 seconds. But this is, again, like it's pseudo real time in the sense it's just not really running in real time. And one thing that we thought, okay, 0.8 seconds is good, but can we really run this operationally? Can we run at least PhaseNet-DAS to pick the earthquake? And the answer is yes, but we are, and it's been running actually quite some time this to see and evaluate also the stability of the code. In particular, I was interested because once we implemented this real-time peaking system, like the day after, we got a magnitude 5.2 here in Southern California in Lamont. This is the location of the main shock. And this series actually of earthquake got quite a bit of aftershocks, and you will see in a second. So this is the earthquake, and this is our DAS array. And these are some of the recording. This is a fairly large time window, as you can see. And this is basically 5 minutes from certain date. And this is the main shock, the 5.2, and then you have a series of aftershocks. And actually, there are way more aftershocks in the middle. Just the scale, time scale doesn't allow to appreciate that. And these are actually travel time peaks obtained by PhaseNet-DAS from the real-time system that I will explain a little bit further later. And but basically, like we have the data come in, and we run PhaseNet-DAS on every single window, and we are able to get these real-time peaks. How does it compare with like a simple LTA, STA LTA? This is the comparison, actually. So some of the main peaks are okay from STA LTA, but as you can imagine, like cars, they generate very strong signal. These are all cars, these diagonal lines, and they're also peaked. So it's true that you can probably like clean up this waveform or peaks using some associator, but it's much more challenging than when you work with fairly nice and correct peaks from machine learning. And that's one of the power of DAS, I would say. And in particular, actually, like as I said, like we only have 18 channels that are streamed, right? So one thing that we're testing now, and I will go into a little bit more detail later in the next slide, if I'm not mistaken, or the one further. But basically, like from these 18 channels, we've that are picked, basically like the picks, we can pick on those 18 channels using the entire array or the 5,000 channel. So you can see that how even if there is a car here, the pick is fairly accurate here. So it doesn't matter if you have like a car noise on top of the cable. And the idea is that what we're doing now is, even though we're only streaming some channel and the picks from some of these channels are, placed into a pick ring, we can still leverage the power and the spatial density of that during the picking process. So that's actually like a very nice, because then it can avoid all the mispicks for potentially cars that are just driving along close to the fiber. So that's one nice thing. And in particular, right now, we're kind of testing on a development system, how we could potentially just have the waveform coming just to archive those waveforms, because it's important to archive those waveforms. But the idea is that actually we're running now this system, we have the same stream of DAS data are processed slightly differently. Like we have 70-second buffer window that has been processed by PhaseNet-DAS. And this process, this peaking, it happens basically about 1.2 seconds. Every 1.2 seconds, we have PhaseNet-DAS running on the 70-second rolling windows. Every second, this window is changing. And the idea what we're trying to see is if we can use those from one channel, we can see if the travel time picks for that channel can be included into the AQMS associator. So basically, like you can leverage DAS almost as if it was a single. Some channels are a single station, but you can still work with the power of DAS of having the entire large scale array for the peaking. So that's actually something that we like a lot. On terms of accuracy, like peaking accuracy, we actually had an intern like Natika Artiaga that is working with us to try to evaluate the effect of DAS and how earthquake locations are affected by DAS or not. And one thing that we did, we had some analysts picking some of the earthquake that were recorded by this DAS system. On the left, you have the PhaseNet-DAS peaks, and on the right, you have analyst peaks. And for P-wave, it's fairly good, actually. In general, like for both are like fairly good. Like for S-wave, you can see it's a little bit broader distribution, but still like very closely related to zero. And by the way, like one thing that this thing can be improved, because we can train with good peaks again and improve PhaseNet-DAS and have a dedicated network or PhaseNet-DAS network running on our model running for this specific system. So this can only improve, but it's already pretty good if you look at this histogram. Now let's change a little bit gear and look at the impact of what would happen if we are able to start recording data on submarine cables in Los Angeles, which is actually like where DAS would have the biggest impact, in my opinion, for earthquake monitoring and early warning, of course. And it happened that actually, like Bill Graves at USGS released some 2 scenarios for large-scale earthquakes happening like somewhat offshore of LA. In particular, like there is this interesting scenario where it's called the Palo Verdes fault that is potentially could generate a realistic magnitude 7.0 earthquake. And these are like some of the simulated waveforms showed in a map view. And these 2 cables are real cables already existing and operating in LA. We don't have access to them yet. Hopefully in the future we will. And they could be instrumented with DAS. And in this part of the presentation, I just want to show the effect of how DAS would improve early warning and monitoring in a sense. And in particular, like from a science perspective, like the ability to also record this kind of signal, this is actually the data that you would get out of this big DAS array. Like this is a 160 kilometer array from the simulated waveform. You could even see actually like somewhat the rupture propagation, and actually like the rupture is propagating along this fault. And one thing that is interesting is the strain rate values here, and that's could be a challenge. We can have a discussion during the Q&A, but I want to just point out that the strain value or strain rate value that we observe from such a large close by earthquake are like about like 2 orders of magnitude of a normal earthquake that we usually record, like a magnitude 2 or 3. So it could be a challenge for other reasons, and I'm happy with like clipping and other things like that. But I mean, this is just, at least it gives a sense of what we have to work with in the future if we plan to do this kind of acquisitions. But assuming that we can actually like get the PGA values from DAS, this is kind of like a somewhat unrealistic. It's 3 component PGAs in this study, but it doesn't really matter. But the point here is the fact that if you perform basically like some early warning system called Finder in for station only, and compare with station plus DAS, you can see that we have a 4-second earlier detection. We have an overall better estimate of the final magnitude, and overall, especially actually, we get like a much nicer and lower warning time or faster warning time, especially for the area of LA close to the coast, as you can see here, where basically most of blue means earlier warning time. So, which is very important. Like these are like some of the metrics that I think that could be important to evaluate before deciding which cable to interrogate, where give priority of some of these systems in a sense. One important piece of the puzzle especially for early warning, but even for earthquake monitoring, when we look at the key, try to estimate magnitude, especially if we want to incorporate DAS and seismic station together, is how we can compute ground motion from DAS. And this is like a nice example experiment that the USGS, Jeff McGuire, did with his team, where basically they have an Arcata, like a DAS array in Arcata, like somewhere north of California, as you can see here. And they placed actually the seismic nodes along the cable, and they compare DAS strain, as you can see here on the y-axis, with node peak velocity. And you can see that there is some kind of nice linear relationship in the log space with these 2 quantities, meaning that potentially we can actually like convert DAS strain into peak velocities, or DAS strain rate into peak ground acceleration in a simple way. First order, of course, is not perfect, but it can give a first order approximation of the ground motion. And in particular, we're trying to see if we can do similar studies here in Los Angeles by looking basically leveraging beside our seismic station also the community seismic network, which is a dense network of the accelerometer. And there are like tons of them close to this cable. This is actually a cable for which we have tons of data. We have almost 2 years of data from this. And so the idea is to try to see if we can see similar behavior and evaluate even further this possibility. And in particular, like if this is working fine, like the idea is to try to do this conversion, potentially also for submarine cable, because here we can find this relationship where we have co-located seismic instrument, but what happens when you go offshore and you don't have this ability? And the idea is to actually, like, under certain approximation, you can actually convert DAS train into, or DAS train rate into acceleration. And there is this paper where they explain how to do it. And effectively, like, what you do, you take some channel and a spatial section of the channel or the array, and you try to estimate the local slope of the waves, and you can convert, as you can see, strain rate into acceleration. And by the way, like, for this specific channel here, we compare with the close by accelerometer, and the overall peak ground acceleration is very similar between the DAS and the converted DAS into the accelerometer. So, which is very, very promising. One last thing before I conclude is about actually try to understand a little bit DAS more, in a sense. And this is some work that I've been doing with Igor here at Caltech in the here in the basement, where we have a shake table that it's used to stretch a piece of fiber. You can see this is a small piece of fiber, and we have an instrument recording data along this fiber. This is a 4-meter long fiber. And here we're trying to see, like, we input a given signal so that we stretch this cable how much we want. We measure actually the displacement. It's not in the picture, but we place actually like a broadband and a strong motion sensor. We can measure the displacement of the shake table very well, so we know how much strain we are inputting, and we can measure the strain from the DAS and evaluate basically the response of the system as function of how much strain, and also like the material that compose the fiber. So we can understand a little bit better how the system works, and try to understand basically ground motion and strong strain relationships. So let me conclude. So we have quite a bit of time to answer questions. DAS could be a transformative technology for seismic network operation in certain cases. And of course, I feel like as we get more DAS system recording, like I think all the data that networks in the future are going to record, they will have a huge impact for scientific discoveries as we make these DAS networks larger and larger. You can see by just, if you look at some of the recent publications, you can see how the impact in science has. The second thing is at SCSN, we are experimenting on with how we can introduce DAS into a real-time earthquake monitoring operation, and I gave a little bit of a flavor of what we're doing from a detailed perspective. And in particular, like we actually implemented a real-time workflow that uses like a SIS standardized DAS channel that can, for selected channel, that can be included into real-time operations. And in particular, I would say, like, thanks to the usage of PhaseNet-DAS, we are evaluating the feasibility of doing real-time DAS earthquake peaking, which seems feasible out of what I showed today. And of course, we would like to thank OptaSense for their support, the California Broadband Cooperative and the LA WDP for accessing their fiber, and of course, the seminar committee for the opportunity to give this presentation. And with that, I thank you for your attention, and I'm happy to take any question. And take a look at what we have, and we have few web pages with a real-time feed from Ridgecrest. Thank you.